All right, let's get started. So it's a pleasure to welcome Izaskun Jiménez-Serra. She's based in the CAB, Center for Astrobiology in Madrid. She was here to give a talk yesterday at the chemistry
Donosti Science.
Yes.
50th anniversary.
And we take advantage of her for a talk on astrochemistry that we don't hear often about. So great that you're around. So Izaskun got her PhD in Madrid at the Istituto de Estructura de la Materia. Then she was a postdoc in Leeds in the UK, then moved to CFA in Harvard, and then in ISO in Munich, in Garching. And then she went to as a Rutherford Fellow in the UK, in the UCL, and then Queen's Mary. And then after that, got back to Madrid.
I managed.
After the yes. And she's an expert on star formation and astrochemistry, and that's what she's going to talk about today. And yeah, she recently got also a consolidator, ERC, so congratulations.
Thank you. Thank you very much, and thank you for the invitation and for the hospitality. It's really been a pleasure to be here, and I'm enjoying very much my stay. So I lived here for a couple of months 10 years ago, so it's great to be back. So thank you very much for the invitation. So my intention today is to give you an overview of the research that we've been doing in the past 5-6 years at the Center of Astrobiology regarding the discovery of new molecular species of prebiotic interest. So what I would like to show you today is how we can connect these detections of these prebiotic molecules with theories of the origin of life. But before I move on, I would like to thank all my collaborators and especially the people in my group, these young people who are really the ones pushing forward this project. And here also what I wanted to highlight is that the interdisciplinarity of this project, because as you can see, we are not only astronomers, but we also collaborate with spectroscopists who basically obtain the millimeter spectroscopy of the molecules that we are interested in the lab, so that we can use that information to look for these molecules in space. We also collaborate with material physicists because what they do, they perform laboratory experiments to investigate the formation or destruction routes, chemical processes of these molecules, or with theoretical chemists. So there are some cases in which these molecules can be synthesized in the lab, and therefore we need to study them theoretically. So that's why we collaborate with all these different people's experts in different disciplines. And then finally, I would like also to thank my collaborators at CAP, who we mainly collaborate with Carlos Briones, who you may know because he's an excellent outreach person, especially regarding in the topic of the origin of life. He's a biochemist. And Jacobo Aguirre, who is an expert on complex network theory. And during the last 5 minutes of my talk, I would like to show you the work that we've been doing recently. So because we are interested in detecting prebiotic molecules, so we first need to step back and then have a look at what life is, which is not an easy concept. Actually, in astrobiology, there was a hot debate during 20 years until everybody agreed on a definition of life. And this is the result. So according to NASA's definition, life is a self-sustaining chemical system capable of Darwinian evolution. So this very simple sentence contains the 3 main properties of life. It has to be a chemical system because it needs to be compartmentalized. It should be self-sustaining because it should be able to perform the metabolic processes. And it should be capable of Darwinian evolution. So it should be able to store and transfer genetic information. And therefore, it should be able to replicate. So during the initial steps of the field of astrobiology, some groups were stating that compartments came first, while others were proposing that metabolism came first, or others were saying, no, replication came first. So what has become clear in the past decade is that the reality is probably something in between. And there is this new theory called prebiotic systems chemistry, which proposes that Earth was a huge chemical reactor in which a high diversity of precursor components were available. And these components progressively turned into metabolic, self-replicating, and membrane-bounded subsystems. So in this scheme here, which was published by Ruiz Mirazo, so as you can see, we can start from these very simple molecules. These molecules react among themselves, forming larger molecular structures, finally biomolecules. And these biomolecules finally end up in these subsystems that coexist and finally yield the first living entity, which we typically call LUCA, the last universal common ancestor. Okay, so what we are interested in, we are astrochemists, we are interested in these initial molecules, in these relatively small molecules, but complex for us, which basically triggered all the sequence towards the origin of life. Now, you have probably heard of the different theories for the origin of life. So there's one possible theory, which is that all these compounds were formed in situ on the surface of primitive Earth, probably in these warm pounds of water, this primordial soup. However, if you look at the different theories or chemical schemes that have been proposed, there's always a place in which some chemical compound needs to be introduced in an ad hoc manner. So this means that these compounds cannot be synthesized in the lab under prebiotic conditions. So that's why some other people suggest, okay, what if these compounds that cannot be synthesized in the lab, what if they come from outer space, no? Which would be something in between some endogenic formation and the panspermia hypothesis, no? So this is our work, that's actually our work hypothesis. Our work hypothesis is that these prebiotic precursors form in outer space. They are transferred to minor bodies of the solar system. So they are transferred to cometesimals, comets, and asteroids. And during the late heavy bombardment period that occurred between 4.1 and 3.8 million years ago, the Earth received a large amounts of this prebiotic material through the impact of these comets and asteroids on the surface of Earth, bringing all the feedstock needed for the first biochemical reactions. And you may be wondering, do these compounds actually survive the atmospheric entrance? And there are some laboratory experiments that show that they do not only survive the atmospheric entrance, but they also survive the impact on the surface. So this is actually a plausible mechanism. So this is actually what we do at the Center of Astrobiology. So we try to establish what of those prebiotic precursors can form in interstellar space and which ones are transferred to these minor bodies of the solar system. So this is the outline of my talk, because I was told that astrochemistry is probably not the field that you typically hear about here. So I am going to give a little bit of introduction about where we typically find these molecules and how are they formed and so on. And then I will move on to the three main fields in my research, which includes the discovery of prebiotic species in space, how these prebiotic molecules are transferred to the initial conditions of solar system formation, which is very relevant for the chemical composition in comets and asteroids. And also, finally, I will mention the complex network theory work that we are doing with Jacobo Aguirre at CAP. Okay, so where do we find these molecules? So these molecules are found in interstellar medium, and as you probably know, interstellar medium is basically the matter that is found in between stars within the same galaxy. So these are 4 images of the Milky Way you're probably familiar with. And the difference is that all of them are taken at different wavelengths. No? So we see them from the optical to the near infrared, mid-infrared, and the far infrared and sublimited. And the main difference is in the optical, you can see that there are dark patches, and those dark patches are molecular clouds. So they are full of molecules and interstellar dust particles. As you know, these interstellar dust particles, they are very efficient at absorbing optical and UV light, and then they re-emit this energy in the far infrared. So that's why the molecular clouds are so bright at millimeter wavelength in the far infrared. The nice thing about these molecular clouds is that they represent protective environments for molecules to form and survive. And as you can see, the typical physical conditions that we are dealing with are very low temperatures, are of the order of 10 Kelvin, and also very low pressure. So we are talking here about vacuum, basically vacuum conditions. And despite these very extreme conditions, as I will show you today, we have a very high level of chemical complexity appearing in interstellar space. How are these molecules formed? Given that we are under vacuum conditions, the only for small molecules, the only thing that molecules can do is to form via bimolecular reactions in the gas phase, either ion neutral or neutral, okay? However, for the large molecules that I'm going to be talking about today, we now know that we need a catalyst, and the perfect catalyst for this is interstellar dust grains. Then this is what we think an interstellar dust grain looks like. Of course, we cannot go outside the solar system and bring one and study it. So this is what we think it looks. So we have a core that is formed of silicates and graphites, and is surrounded by this ice cover, which is mainly composed of water. And it also has some impurities, which are the molecules that you see there. And these impurities, even though they represent orders of magnitude, or they have abundances orders of magnitude lower than water, they are really key for the formation of these larger molecules. Now, these grains, as you can see, the surface of these dust grains, the ices, are affected by different chemical processes. So the atoms can diffuse, radicals can also diffuse and react and form larger species. They also receive radiation from UV photons and cosmic rays, so that impinge energy on the ices. And the ices can also be heated by protostars. Okay, so these interstellar dust can be processed in many ways, forming larger and larger molecules. So how do we detect these molecules? So interstellar dust grains, so imagine they form all these molecules in the ices, and once they are heated by protostars, these ices get sublimated. Okay, so then they get sublimated and they go back into the gas phase. And that's when we can observe these molecules. And we observe these molecules via their molecular rotational transitions, okay, which is what it is shown here. So for a molecule, small molecule such as carbon monoxide, which is the most abundant molecule after H2 in the universe. So you see that its rotational spectrum is very simple. However, if we increase the number of atoms in the structure, which is, for example, in this case, is the urea, you see that the millimeter spectrum of this molecule really gets very complicated. And you need to think that in order to provide a robust identification of a molecule in space, we really need to look for all the transitions. So we at least need to have 10 of these rotational transitions clean, that we are sure that those transitions are there, okay? So things become very complicated. So when I showed this to a chemist, so yesterday I was a little bit worried. I was saying that urea is complex, but then this is nothing, no, it's peanuts. But for us, it's really complicated in this. Okay, so we astrochemists are interested in linking the chemistry that we see in space, which is simple, with the complex chemistry that we see in life. And we think that the link is provided by what we call complex organic molecules, which I probably mentioned already several times. But what do we mean by a complex organic molecule? So we just imposed a convention for us as chemists, and then we said that complex organic molecule is any carbon-based compound with at least 6 atoms in its structure. And why 6? Well, methanol is the most abundant complex organic molecule in space, and methanol has 6 atoms. So that's basically the reasoning behind it, okay? So it's just a convention. And here I show you some examples of complex organic molecules that now are routinely detected in space. So wherever we look at, we see these complex organic molecules. No? So it gives you an idea of the type of compounds that we detect. And actually, these compounds, you find them in your daily life. So this is, for instance, is what it is used in refrigerant, in the fridge, no? So it's a liquid. Glycolaldehyde is actually sugar. Ethanol is what you drink in a beer, alcoholic drinks, and the methyl ether is a fuel. Okay, so these type of molecules you find them in your day-to-day life. Okay, so where do we find complex organic molecules in space? Well, actually, thanks to the advent of new instrumentation, especially high sensitivity instrumentation, it's become clear in the past 20 years that complex organic molecules are ubiquitous in interstellar medium. So wherever we look at, there we are going to find a complex organic molecule. So chemical complexity is inherent or is ubiquitous in space. So these complex organic molecules, however, were first detected in star-forming regions because for obvious reasons, because they were sources that were very bright, because there was protostellar activity, they could evaporate the ices from dust grains, injecting a lot of these molecules that could become available in the gas phase for us to look at. And because they presented very large columns of material, okay, along the line of sight. So that's why we were using this type of objects. So they were hot sources, no? We were saying hot sources. And this is basically the progression, the detection of these complex organic molecules with time. And as you can see, there was a steady progression, no, of detections, okay? Now, about 5-6 years ago, there was a change in the game, a huge change in the game, because some other groups started observing, including us, started observing these other types of sources, which I will call them cold. No, they are molecular clouds whose physical conditions indicate that these molecules are going to emit at lower frequencies, okay? And this type of objects are cold molecular clouds, which I will show you in a minute, and the giant molecular clouds that we can find in the Galactic Center. And these really represented a huge change, okay? When you see that when we started observing this type of objects, we had this boost in the detection, the discovery of these complex organic molecules. Okay, and then some examples can be seen from the work of Pepe Cernicharo, who is also in Madrid, using the Yebes 40-meter telescope, and especially the Quixote survey, and Brett McGuire at the MIT using the Green Band telescope. These are two competing groups that are giving a lot of activity in the field. They are competing directly. And they observed exactly the same position in the Torres molecular cloud, this TMC1 Thermopoline peak. And they performed these very deep integrations. So in the case of Pepe's, which is the one that I know better, they have integrated 1,500 hours on this particular position, okay? So this, of course, has provided an ultra-sensitive broadband spectral survey at 7 millimeters, which is an amazing survey, and the same for the MIT group. And as you can see, these are the type of structures that were detected in 2021. But just to give you an update of the latest one that they claim they have detected is this one with 7 rings, okay? So we are achieving a much, much higher level of complexity progressively, thanks to this high sensitivity instrumentation and the sensitive spectral surveys.
Sorry, Izaskun.
Yes.
Are you in Zoom?
Or how are
In
they?
principle, yes.
They said that they see only 10% of the screen.
That I don't know.
Taking the
Okay, maybe it's this.
But can they hear me at least? Do they hear me? No.
People online, can you hear? We don't know.
God, if I have to repeat everything.
No. I can also log in to see how it is. Sorry to interrupt.
That's okay. So shall I share again, maybe? And see? Probably the easiest, no?
Sure, you can try.
Let's try. Okay, so if I share desktop 2, and then I come here. What now?
Yeah, I don't know. No one here is connected, right? We check. We try to connect. Let's just go on and then.
Basic sense loading we learn about it. It's the
We'll continue. It's fine.
Yeah, it's enough?
Yeah.
Okay.
Yeah. Well, let's try it.
Yeah. Okay.
You can see fine. Okay.
As I was saying, so this is basically the latest, molecules that I have reported with these 7 rings. So you can have an idea of the level of complexity that this field is approaching. Okay. Now, what is the reason for this? So the reason for this is that because the concept has completely changed. Knowing the hot sources that were tackled at the beginning before 2020, we had relatively high temperatures, and this makes the spectrum of complex organic molecules such as glycine is shifted towards higher frequencies. Now, what happens is that simpler species are going to start emitting from 80 gigahertz upwards. So, and then therefore, so all this part of the spectrum is going to be much more, it's going to be much more complicated, and there are going to be many more lines appearing in that part of the spectrum. If we go to what we call the cold sources, okay, so what happens is that the spectrum of these molecules is going to shift towards lower frequencies, and these lower frequencies are cleaner from the transitions from simpler species, and this significantly reduces the level of line blending and line confusion. Okay, so that's why it is much easier to detect these molecules at lower frequencies than at higher frequencies, and this is when these telescopes such as the Yebes 40-meter and the Yebes, which operate at these lower frequencies, really have excelled in this field. Okay. So this is basically the approach that we have also followed. However, we have completely changed the type of astronomical source. So the sources that we have used are the giant molecular clouds that we can find in the Galactic Center. So this is an image that you are probably very familiar with, obtained towards the central molecular zone. And as you know, there are many, there's a chain of giant molecular clouds. There's a lot of molecular gas around. We have the Galactic Center. We have also these non-thermal filaments, which we think are probing the magnetic fields. There's also a huge outflow. It's probably related to a past activity of the central black hole. So that's a beautiful image, no? So, but also the important thing is that the CMZ, or the Galactic Center, hosts more than 80% of the dense gas. Okay, why is this important? This is important because we are going to have large columns of material along the line of sight, and this is going to enhance our chances of detecting these molecules if they are present. The region that we have targeted is this molecular cloud complex in Sagittarius B2, and in particular this position G0693, which is located, so if you're familiar with Sagittarius B2, the shape that it has this shape, and this is the position, it's basically the brightest spot in the molecular cloud. And what we think is happening in this position is that there is a larger scale interaction between two flows of molecular gas, and this is causing this brightness in this methanol maser, which is an excellent probe of shocks, of MHD shocks, and also the chemical complexity. Now, you may think, okay, this is not a cold source. And I would say, exactly, this is not a cold source because the typical temperatures of the gas, what we call the kinetic temperatures, are high, are of the order between 70 and 150 Kelvin. What happens here is that the densities are low. And this causes the molecules to populate only the lower levels, okay? The lower energy levels, and that's why we have a low excitation temperature, which is what we are interested in. So this is the excitation temperature, is what we causes the spectrum to shift towards lower frequencies. And this is what we use in our favor for the detection of our molecules, okay? So this is an example of the spectroscopic survey that we have taken in the past 5-6 years. So we have used several telescopes, the Green Bank telescope at lower frequencies, but here I'm only showing the spectroscopic survey taken at 7 millimeters with the Yebes 40-meter telescope, and the 3 millimeter and 2 millimeters parts of the spectroscopic surveys taken at IRAM 30-meter. We also have the 1 millimeter part, and even beyond the 1 millimeter part to the sub-millimeter part with APEX. in Chile. And the analysis of all these spectroscopic surveys have provided detections of more than 170 species, out of which 50% out of which are complex organic molecules. So this is basically, the source represents the Rosetta Stone in astrochemistry. So whatever molecule you think of, you just go to this survey, and there it is. Not everyone, because there are some that we don't detect, but many of those that you can think of, it is there.
Izaskun, sorry.
Yes.
Do you mind if
Yeah, no.
all these lines, so these are all
All are molecular lines.
they're all molecular.
They are all molecular lines.
There is no contamination here from something else.
Well, there are also hydrogen radio recombination lines, but that we have also identified, and they are very well identified. But all of those are molecular lines. So what we do also, so we perform also some methods when we perform the observations to avoid interferences or any feature coming from the electronics of the telescope. So what we do is we use two different frequencies, and we overlap the two spectra taken at the two different frequencies, and that's how we can identify spurious lines that we get rid of. Yes. But all these that you can see is all those molecular lines. And even if you zoom in, I should have shown a zoom in. So if you zoom in here, very close to the node, it's still full of lines. Okay. Yes.
I have a related question. If you have a molecular cloud with multiple molecular species in it, can you really distinguish the different spectra of those same species at the same location?
Yes, because so you need to think that each molecule has its own spectrum and is unique for that molecule. It may be that, by chance, so there are two transitions, from different species coinciding, overlapping, right? But what we do is we fit, so by assuming local thermodynamic equilibrium, we fit all the lines from each molecule, and we actually have our own software that we have developed, and we have a long list of more than 330 molecules that we have fitted all of them, okay? And we overlay the predicted spectrum on top of the data, and we perfectly know which transition and what other molecules may be contaminating that transition. Okay, so that's how we are sure that when we make a detection, we claim a detection, we need to have at least, as what I said before, 10 transitions that are clean, clean in the sense that they do not show any contamination from any other molecular species. Okay, yes? Okay, so what molecules do we target? Okay, so this is what I started when I arrived at the Center of Astrobiology, and then when talking to Carlos Briones, who is an expert in this field, then he pointed out these works by the group of Sutherland in Cambridge, and in particular, so this chemical scheme belongs to this paper published in Nature Chemistry by Patel in 2015. And as you can see here, by starting from very relatively simple molecules in this work, they could build up this whole chemical scheme forming not only primitive ribonucleotides, but also sugar and lipid precursors and amino acids. Okay, so by just starting from this very simple molecule, they could basically build up create all the building blocks of life. Then what we decided then was to start having a look at the beginning of this chemical scheme, because this is what we could reach at that point. And then in blue, I'm just showing the molecules that were routinely detected in 2019. And in red, the molecules that had not been detected up to that day. So we were very happy when we realized that we have the detection of glycolonatride, which is this intermediate species in the formation of sugars with 3 and 4 carbon atoms. And encouraged by this, then we decided to continue looking for the rest of species. So we targeted urea, which is this one, 2-aminoxazole, which is a key intermediate in the formation of pyrimidine ribonucleotides, and also these sugars with 3 carbon atoms. So these first searches were done with very preliminary surveys with little sensitivity. Showed that we didn't have any detection of glyceraldehyde and dihydroxyacetone, these sugars with 3 carbon atoms. However, urea was there. And we were a little bit late because Arnaud Beloche from the Max Planck in Bonn reported the detection a couple of months before us. But at least, so this really showed that urea can be found also in the interstellar space, and demonstrated that this type of molecules, prebiotic molecules, can be found under these extreme conditions. We also looked for 2-aminoxazole without any success. And I have to say that this molecule is actually very complicated. So to detect it now, even in our very sensitive spectral surveys, we still don't see it. And actually, this was the trigger of these laboratory experiments that were performed by Belén Matea and Víctor Herrero at the Instituto de Estructura de la Materia. And here, what they perform, they use what we call interstellar ice analogs. So they basically build up ices that simulate or that with the same physical properties of interstellar ice. But for that, we use either pure 2-aminoxazole or urea ices, or we mix it with water. And what they did is, so they built up the ices and then they irradiated these ices with UV photons or with a high energy electron simulating the interaction of cosmic rays. And what they found in these experiments that urea is much more resilient than 2-aminoxazole. So this may explain why we see urea and we don't see 2-aminoxazole. So this actually is very useful because we know which one of these two is going to survive on the surface of minor bodies of the solar system, of asteroids and comets. Because if they are very sensitive to UV radiation, those species won't survive on the surface of those objects. A little bit later on, there was this other work of Becker in 2019, and this is from the group of Thomas Carroll in Munich, where they showed that they could form both pyrimidine and fluorine ribonucleotides in the same primordial soup, starting also from simple molecules. And if you inspect these first molecules, you see urea, but also hydroxylamine. So because we had detected urea, we said, okay, why don't we look for hydroxylamine? And this was also detected in 2020, and this was the work of Victor Revilla, who is a Ramón y Cajal fellow in my group. And this really was a confirmation that the method that we were using was really powerful, because we were reporting, or we were discovering all the molecules that we were interested in and which are involved in these prebiotic chemical schemes. And since then, we have reported the detection of 25 new interstellar molecules that include precursors of ribonucleotides, precursors of sugars, of amino acids, also precursors of proto-lipids and proto-proteins. So this is something that we are currently doing. We are improving the sensitivity in our spectral surveys, and this is something that we plan to explore in the future, in future years. Now, I'll mention just the last one, because this, if you have been following up on the detection of this biomarker proposed by Niku Madhusudan in this exoplanet, this Haitian world K218d. Have you heard about this in the news? No? So it was, there was a lot of information in the news about this discovery. And basically in this work, what they proposed is they had confirmation of this dimethyl sulfide molecule, which is there. So it has two methyl groups, CH3, CH3, and then the sulfur in the middle. And apparently, so this molecule can only, or is formed by the activity of some bacteria in oceans. Then what I would like to mention here is that we need to be very careful at saying that these kind of molecules are unambiguous biomarkers, because we reported the detection in interstellar space just a couple of months ago. So this means that these molecules can also form abiotically. And of course, they can be transferred to comets, which is also what was reported the year before in comet 67P. So there is an exogenous source for this molecule that we should also consider when we find this type of molecules in exoplanets. Okay, so just would like just to say a word of caution before going and saying that we have detected life in exoplanets. So be careful with that kind of statements. Okay, So of course, because we are detecting new molecules and we know very little about their chemistry, this has triggered a lot of theoretical works to try to understand the chemistry of all these species. And for this, this is the work of Juan García de la Concepción, who was a former postdoc that I had at CAP, and Germán Mopeceres, who is at the Instituto de Física Fundamental in Madrid. And they have been trying to study all these, the chemistry of these species, either in the gas phase or on the surface of that screen. So if you're interested, you can go and have a look at. And the last thing that Juan is interested in is in trying to understand whether these chiral structures can form on the surface of dust grains, to try to understand whether the issue of homochirality in life. Okay, I don't know how much time do I have. Yeah, I have a little bit more.
10 more minutes.
10 more minutes? Okay. So I'll go fast about this. So now that we know that these prebiotic molecules can form in interstellar space, we want to understand whether they can be transferred to these protoplanetary systems, and especially whether they can be locked into comets and asteroids, right? So you know that the formation of a planetary system goes from molecular clouds, then we form the protostar that is fed through the circumstellar disk, that the outflows, in order to preserve the angular momentum, they need to clear, so they need to eject outflows, they clear up the envelope, leaving the protoplanetary disk that finally loses its gas, and then there are some planetesimals and cometesimals forming, and then we have the planetary system at the end. Then if we want to know the transfer, how much of those prebiotic material is transferred to protoplanetary systems, our approach is to focus on the initial conditions. So we want to know how much of the material is locked into what we call the prestellar core, which is the initial core that is gravitationally collapsing. Why is this? This is important because we know that the chemical composition found in comets actually come from that stage, from the prestellar stage, okay? And this is what it is shown here in this diagram, comparing or calculating the ratio of deuterium over hydrogen. And as you can see here, this ratio is enhanced compared to the value of the protosolar nebula. And this is one of the reasons why we think that the water that we see in our oceans has been brought to Earth by the impact of comets and asteroids, okay? So that's why we are focusing on this prestellar stage. In our work, so we started focusing on this particular prestellar core, F1544, which is a prototypical prestellar core. It has been studied to a high level of detail. So what we did for the first time, and this was back in 2016, was to perform the highest sensitivity observations towards this core, towards two positions, so the central position here, and a position which was a little bit off, and which represented basically the peak of the methanol emission. So we thought, okay, so if the methanol peaks here, other complex organic molecules may be present. So we performed these high sensitivity observations. We spent tens of hours, 30 hours, 35 hours on each position. So this project was very expensive observationally, but it paid off because we reported the detection of these complex organic molecules in both positions. And we saw clearly that there was an enhancement in the outer shells of the core, which actually, if you have a look at the linear distances of this outer shell, corresponded to what it would be the Oort cloud in our solar system. Okay, so that means that there's an enhancement of this complex organic material in the equivalent Oort cloud region in this prestellar core system. And why is this enhancement? What is causing this enhancement? This enhancement is being caused simply because carbon monoxide, which is the precursor of all these complex organic molecules, starts being depleted catastrophically at this particular distance from the core. And this is what is shown here. So this, where the dip in the abundance of CO is happening, is right at that distance. So what we are probing with our observations is what we call the CO freeze out, the snow line, the CO snow line in prestellar cores. And this is what is triggering this active chemistry on the surface of dust grains. Doing this methanol at this particular position in this outer shell? And the answer is yes. So these were preliminary observations that we did with the IRTF, so here from the ground. And as you can see in these observations, we reported an abundance of about 11% of methanol with respect to water, which is actually one of the highest reported in this type of cores. And now what we're going to do is to repeat this, but with the James Webb, so that we can also detect larger molecules towards this outer shell of L1544. But because we didn't have the JWST observations, then what we did was to use the ISH observation that was part of the collaboration. This was an early release science program, in which the goal was basically to probe the chemical ice composition along the formation of a planetary system, going from the initial conditions in the molecular cloud, the protostellar core, going through the different phases, the protostellar phases, from the class 0, class 1 to the class 2. Here with the disk, here you see the disk and the jet. This is the image that we obtained with the JWST, beautiful image of the cloud, which is the chameleon-1 molecular cloud. And these were the first spectra that were reported. This was the project was Melissa McClure, the PI, and these spectra were published in the first publication by her in 2023. And we reported here the spectra taken towards two very high extinction positions in the cloud. These are basically the highest extinction positions that have been targeted with this kind of observations. So we could probe for the first time the chemical complexity of ices in these positions. The nice thing is that we also detected COMs in these initial conditions in the molecular cloud, which really showed that the chemical complexity already builds up at the initial conditions of a star formation. And that gives actually some justification for how we see that chemical complexity later on in comets and asteroids. And the plan is to expand this by using the archive available at provided by the James Webb. And for this, because we are going to have hundreds of stars available in the data archive, my student Andres Mejias has developed this new analysis tool they call AI's Automatic Ice Composition Estimator, which by using neural networks, he has trained a neural network to try to analyze the spectra coming from the James Webb and to provide the chemical composition of ices. So this was the first comparison with the two sources observed within the ISH program, and the results are very promising. So this is something that we plan to explore in the future. And in the past 5 minutes, then I would like to mention also the work that I've been doing regarding the complex network theory, which was a project that I also started with Jacobo when I arrived at the Center of Astrobiology. And this does not have anything to do with chemistry, which is nice. And but the approach was to use a completely different perspective. So what we wanted to do was to use a complex network of networks and to try to see whether we can simulate the chemistry without putting any chemistry in the framework. So we just used complex network theory and game theory. And what we did was we started from nodes, which basically is equivalent to the atoms. We allow the nodes to interact, given a certain probability, to interact and to destroy. So they can create bonds or they can destroy bonds. And the probability of creating and destroying bonds is given, or depends on this parameter, which is beta, which is related to basically to the environment. So if you have a harsh environment, then you have a lower beta. If you have a less harsh environment, you have higher values of beta. Then what we found, so this is the simulation, you see, so you start with nodes, single nodes, you start forming two systems with 2 nodes, 3, etc. And then at a certain point, you start seeing complexity, which is what it is represented here, no? So the number of configurations. Above a certain critical value of beta, chemical complexity explodes. So the nice thing about this, of course, this framework can be, which is called Melwell, by the way, it can be applied to any complex system that you can think of. But the nice thing about this work was that we tried to apply it with astrochemistry. And then in here, what we did was to compare the outcome of Networld, which is shown here, with the astronomical observations that we have towards molecular clouds with different levels of extinction. So there's no fit, there's nothing. So it's just a pure comparison between the results of NetWorld and the observations. And as you can see, the behavior of the abundances of this molecule resemble very well the predictions of NetWorld. So what we think is that the emergence of chemical complexity is basically ruled by universal laws or by universal rules. And this is something that we plan to explore in the future by making NetWorld a little bit closer to actual chemistry, to the real chemistry, to see whether we can improve it. And all this that I've told you about is what we will be doing in OPENS, which is this ERC consolidator grant recently obtained, in which we will study what prebiotic molecules we can find in space, which ones are transferred to the parental molecular core, and to try to understand the emergence of chemical complexity. And just to acknowledge the funding, and if you have any questions, I'll be happy to answer. So thank you very much for your attention.
Thanks, very nice. Questions? Lourdes.
Yeah, I guess maybe related to this last part that you were saying. So as far as I understood, at least the hypothesis is that for life to appear, you get this complex chemical organic molecules. So I was thinking but those for those to create, you need some conditions in given space. Like you need dust and you need So I was thinking whether joining that to maybe what we know from cosmology or we know from astrophysics, can you put an upper limit of at what point in the evolution of the universe life was possible to be created?
Nice. So that's something that we want to explore with NetWorld. So with NetWorld, the idea is basically, what we want to do now, we want NetWorld to evolve and then to start injecting the different elements along the evolution of the system to see whether we can actually provide some constraints on that. So on how chemical complexity starts boosting at a certain point in that cosmic evolution. Okay, but observationally, what I can say is that we have detected water up to a redshift of 6. I think that was the highest redshift so far. And you need to consider that water can only be formed on the surface of dust grains. So you see water at redshift 6, you have grains, and that means that you have also complex chemistry for sure. Okay, it's a long. So I think there you really need to, of course, employ ALMA, so perform very high sensitivity observations instruments to obtain these high sensitivity spectrum to look for these complex organic molecules. But these complex organic molecules, we see them in nearby galaxies now. In all these surveys that have been done with ALMA, they appear everywhere in the nuclei, in the galactic nuclei of these galaxies. They all are there. Yes.
Have a similar a question in a similar way, let's say. So regarding redshift, this game that we can see back in time essentially. So can we target? Do we have the sensitivity or we will have to target galaxies 5 giga-years ago and see what are the conditions there at which a solar system like our own formed?
The sensitivity, I think the problem there is sensitivity.
Because all of these lines, they were here in cool cores in the central molecular zone.
I mean, we can use as a probe, so we can use the molecular clouds in the Galactic Center. No, so the Galactic Center giant molecular clouds are basically the best template. No, that is actually found in other external galaxies. So if we target these external galaxies, so most of the emission is going to come from the nucleus, from these giant molecular clouds in the galactic nuclei. But there, the problem is the sensitivity. So with ALMA, it's very challenging. It's very, very difficult. All the instruments, because the higher you go in redshift, the lower you go in frequency, because it's inversely proportional to 1 + z. So you need to go to lower frequencies. There, the square kilometer array, I don't think it's going to have the sensitivity. One possibility is the NG-VLA. The next generation VLA, which is going to be much more sensitive than the SK. But for that, we need to wait, long, because I think it hasn't been approved yet. No?
Okay.
So, but with the SK, I don't think it is possible.
Diego and then Francisco.
So I was wondering if these complex organic molecules like survive in the protoplanetary disk, like when they collapse.
Yes, yeah. Yeah, they survive and we see them. So the problem is with protoplanetary disks is that because they are so dense that most of the molecular gas or most of the molecules are depleted, are frozen on interstellar ices. So we don't see them in the gas phase. So that's why they are so difficult to detect. However, you can play a trick. And what people have been doing is to use these FU Orionis stars, which suffer these outbursts, periodic outbursts. And whenever you have an outburst, so all these molecules frozen on interstellar dust grains go back into the gas phase, and that's when you can see them. And we see these complex organic molecules, all of them, the ones that I've shown you, not the prebiotic though, because the prebiotic are very difficult to observe, but in principle, with higher sensitivity, we should be able to tackle them. But the first one that I show you, the ethanol, glycolaldehyde, the ones that I show you that you find them in your daily life, those are readily detected in these kind of objects.
Francisco, then okay. Francisco and then you, Emilio. Okay.
Okay, yeah. So I was interested, so you showed these net flows calculations. The
net world,
sorry,
Networld?
I got confused with the name, yeah.
a lot of flows.
So that depending on the beta parameter, they kind of are able to predict the abundance of these molecules, right? So does this now allow you to, let's say, try to measure, for example, the beta parameter of these exoplanet atmospheres and then play the game of whether the abundance of these molecules that they have detected is consistent with, because I guess net flows kind of shows you more or less how much of these molecules you can form just by simple random association of atoms, right? Net worlds, sorry. So does this allow you to perhaps disentangle this? Because I guess...
Okay, there, for exoplanets, I haven't thought of it, to be honest. So I think this is something that we...
the detection of the dimethyl.
Yeah, or dimethyl ether.
That it gets also produced, I guess, through a process like this one, right?
Yeah, I mean, in principle, so, the chemistry in an exoplanet atmosphere is also a complex network. So in principle, so the same principles should apply, no? There, so the answer in principle is yes. So you could do that. However, I don't know whether, in that case, it would be better to use, dedicated models that do exist to predict the chemistry. So the actual chemistry that is formed in these exoplanets. Here, so you need to think that here, so we are forming structures, no? And here we are just comparing the ranking, no, of abundances with the number of atoms, no, the number of nodes, okay? That's the comparison. So we are not making a one-to-one comparison between the actual structure of the molecule and the structure formed in that world. That's something that we plan to do in the future, to see whether some certain structures are favored over others, which can actually give us a hint or give us information about what kind of molecule we should look for in space. Okay. But I think for your question, probably, if you're interested in that, it's probably better to use dedicated modeling that performs, in that case, it would be 3-body reactions in simulating the chemistry of the atmosphere. We are interested in one particular molecule.
Yeah. So that was really intriguing. I was interested in your comment about resilience against some forms of radiation. You mentioned high energy electrons, UV as well, and so on. I can imagine that some of the typical cosmic radiations that you have around would completely annihilate these molecules if there is a collision event. I don't know, how frequent are they? What makes them make this urea resilient, etc. So if you could elaborate a little bit more on that. And whether any of the things you see could be somehow induced by any of these events.
Okay. So let me see, there are many questions in there. So let's start. So in the Galactic Center in particular, so we know that we have an enhanced cosmic ray ionization rate. And we think that that actually plays a key role in the detection of these complex organic molecules, because that injects a lot of energy into the medium. And you need to think that cosmic rays can affect the chemistry of grains either by direct impact, which locally hit the dust grain or the ice, or we have a secondary effect, which is the production of secondary UV photons. So cosmic ray impacts an H2 molecule, which is excited, and then when it excites, it produces a UV radiation field. And that's how it can also affect the chemistry on the grain. Why urea is more resilient? That is probably due to the chemical structure and to the bonds, basically the structure of the molecule. If you go to 2-aminoxazole, it is a cyclic molecule, but it also has a bond with NH2. So that bond is very fragile. And that's why you don't see it. So it's probably that bond is weak, so it can get destroyed by either UV photons or this effect of high electron simulating cosmic rays. So if that bond is destroyed, you don't see it any longer. So that's why probably urea is more resilient because of that. Yeah, did I answer all the questions? Yes.
Well, any of it could be partly catalyzed by any of this radiation?
Yeah. So actually the cosmic rays, so because they impact the surface and they inject energy locally, they can transfer energy to radicals, which are present on the surface, and then these radicals can approach to each other, or they can diffuse on the surface, they approach and they form larger molecules.
Okay. Daniele, you and then
Thanks.
Go.
Thanks for the very nice talk. I think this question is kind of related to the previous one. So you showed a diagram in which complexity kind of exploded, you said, after a given beta critic.
Right? Yes.
So I was wondering if the fact that the system is in itself complex somehow is enough to say that then some sort of structure, chemical specific complexity would emerge. So what I'm saying is maybe you can imagine hyper-complex molecules, but then maybe these are not what you need to form life or to have a basis for life. So I was wondering if complexity itself is a measure of the fact that, the fact that complexity emerges is itself enough to say that life would emerge?
No.
Okay.
You're right. So, and one of the challenges now in prebiotic chemistry, so it's a condition. So you need to have chemical complexity, no? That's for sure. But that's one of the challenges that now in prebiotic chemistry, all these people working in the lab are facing, that when you introduce the ingredients, no? What you form in this prebiotic soup is a wide variety of compounds, out of which only a very small fraction is used by life, no? So here the problem is how from that large variety, wide battery of compounds, no? How life selects the ones that are needed, no? For the development of the first biomolecules, of the first subsystems that actually have functionality. So that's the key there, no? The key is how do you choose those compounds that will give you a functionality, that will give you a function. Okay?
Yeah.
So that's the trick. So that's what we really need to look for in the future. And that's something that not myself, because that's a bit way off my field. But Jacobo Aguirre and his group, that's actually something that they are exploring.
Okay.
How the first metabolic cycles are produced, also using network. Yeah.
Okay. So, yeah.
Okay, so you made an assertion that the introduction of these prebiotic molecules of life which were made in space into the Earth was 4.5 to 4.1 million years ago, which was common knowledge by now. So I'm wondering if you could look at this from a temporal evolution perspective, because you have detected these complex organic molecules in space already. So if working backwards from you say it starts from molecular clouds all the way to star-forming regions, then proto-planetary disk, then to the planetary system. So can you sort of work from its introduction into the planetary system from the time that detected, if you can figure out how much time that takes so that it can help in the understanding of when life actually started, because in the prebiotic sense. So is it possible to do that?
So the age of our sun, no, I think is 4.5 billion years, no?
Yeah.
And at that time, so you need to think that all these processes from molecular clouds to the formation of planets takes about 10 million years, okay, before then. But here, so what I'm trying to highlight is that, so we are trying to make the connection between the chemistry that we see in the interstellar medium with the chemistry that we see in comets, so in our own solar system. Okay, so here the point is, if you see that chemistry in the interstellar medium, that means that chemistry or those compounds will go into other planetary systems. So it's not, so to provide some constraints on our solar system. So what we are trying to say is that chemical complexity is ubiquitous in the universe. And if it happened in our solar system, no, because we see that there are commonalities, there are similarities with the chemistry that we see in comets and asteroids, it has to happen for other future planetary systems. Yeah.
Okay.
Thank you very much for a very nice talk. Just to this part, can you comment how this theory basically compares with this assembly theory by Izaskun they published several years ago? Do you have?
I don't know. I think we probably need to, if you want, so we can talk later on, because I'm not aware of so here the expert on complex network theory is Jacobo. So I provided the astronomical part. So but he's probably, but if you want, so we can chat and then I can ask Jacobo.
Yeah. Okay, last question here, then we ask online.
I'm wondering if all of the molecules that we detect in space are ones that we can study in the lab on Earth and then we know exactly the transition, or if it's possible that there's molecules in space that there are different conditions in the clouds that are ones that we actually can't create here, and then how would we detect any potential new molecular composition?
Okay, so let me see if I can rephrase the question. So is it possible to have laboratory experiments that study what are the most likely species to be detected in space under interstellar conditions?
That's related, but slightly different.
No, so I ask again, because
I guess the point is, are there emission or something that you cannot reproduce in the lab? So it can only be created in space, or you don't know how to reproduce in the lab?
Yeah.
Would that be a bit?
Whether you can create structures in space that you don't know about.
Yeah.
No? Okay, no, well, so that's a limit. So actually, if you have a look at the spectroscopic surveys that we have basically identified 50% of the features. So the other 50% remain unidentified. So that's something that we are doing step by step. So we are obtaining the spectroscopy. That's why we collaborate with so many groups, experts in spectroscopy, because we say, okay, what if you look for this model, or can you calculate, or can you obtain in the lab the spectrum for this particular molecule? And we can go to the spectra and then check. But there, yes, so I think there are other things that you can think of. I don't know, I was thinking about this crazy idea of using artificial intelligence, to see what kind of favored structures would be present under interstellar conditions. But I think that needs to be thought twice, because you need to train these algorithms and so on with something.
That's what I was thinking.
That
Because
is-
you train them on laboratory data, but what if there are things that you can study in
Exactly.
the lab?
But then your training data set is completely biased.
Yeah.
No, so that's a limitation. No, but but it's an idea. So it's an idea that's hanging around. But yes, yeah, it has its limitations, but it's something that we can think of. Yes, we can think about in the future. Yes.
All right, let's ask online. I forgot if anyone online wants to speak. Just speak up because I don't see hands.
There's a line.
Okay, well, in case you can also send an email to Izaskun. Yes, there is any question. Okay, I think we can close here. Thanks a lot. Very, very.
Thank you.